Stoichiometry. It's the chapter number 1. The learning objectives are, we are going to understand what is stoichiometry, what is the need and use of balanced chemical equation in stoichiometry. We are going to understand moles and Avogadro's number interconversion, moles and mass interconversion. Now first let us look at what is stoichiometry. Stoichiometry is originated from a Greek letters. Stoichio comes from stoichion, which means element, and metry comes from metrion, which means measurement of element in a chemical equation or in any chemical reaction setup. That is known as stoichiometry. It works best with balanced chemical equation. This also gives the liberty to the scientist to find out that what amount of each reactant is needed to produce a certain amount of product. It's the same way as a cook has to cook a certain amount of dish, so he or she knows that what amount of each ingredient that are needed to cook that dish is needed to make that particular amount of the dish he or she has to cook. It is the same way that if I have to cook a dish for 10 people and on the other side I have to cook a dish for 2 peoples. So we are very much clear that for 10 peoples it will be a large amount of food that we have to cook. But for 2 peoples we have to produce a small amount of dish. So stoichiometry works with the amount of substances. We can also go deep down and works with the amount of elements which are present in a larger amount of the substances or in a smaller amount of substances. So it's not only about the measurement of the amount of substance in molecules or in compounds. It can also works with the elements, the particular amount of element within the molecule which is present and which is used in the reactants to produce product, and that product contains how much of that particular element we can find out from the stoichiometry. So this stoichiometry is used as a quantitative analytical tool of the reaction. Now let us look at balanced chemical equation. What actually is balanced chemical equation? So balanced chemical equation, let us take an example. There is this reaction in which nitrogen reacts with hydrogen to produce ammonia. This reaction has its industrial importance, and that this reaction is known as Haber's process, which is used to produce ammonia. If we look at this reaction, we see that there are 2 atoms of nitrogen here. There are 2 atoms of hydrogen here, but here we have 1 atom of nitrogen and we have 3 atoms of hydrogen. If we look at the law of mass conversion, we can see that mass can neither be created nor destroyed, but it remains the same throughout the whole reaction. And how? Because different atoms, they combines in a different ratio and they make other molecules. But if we add up the mass of those molecules, we will end up with the same amount of mass. So mass can neither be destroyed and can neither be created. It is present among us. We just convert it into different substances. Like here it is nitrogen, which is a gas, but now it is converted into an ammonia, which is also a gas, but the 2 of them, they are quite different from each other. Nitrogen has no smell, whereas ammonia has an astringent smell, and the same goes with the hydrogen. So we need to balance the amount of nitrogen and hydrogen on each side. So how we balance the equation? The only rule to balance the equation is to make odd one even. So here we have the most odd one, that is ammonia. So if we multiply it by 2, that becomes even. Now we will have 2 of the nitrogen, we will have 6 of the hydrogens. So this will take a shape like we will going to have 2 nitrogen atoms here, and we are going to have 6 hydrogen atoms here. Now the nitrogen is balanced on each side. We can see that it is balanced on each side. The only thing that is imbalanced now, that is 6 hydrogens. So how to make this balance? In order to make 6 out of 2, so we multiply it by 3, and now we have 6 hydrogens. You see, the equation is balanced. Now this equation tells us that, if we rewrite the equation, this equation tells us that 1 molecule of nitrogen is reacting with 3 molecules of hydrogen, and this is going to produce 2 molecules of ammonia. So we see that it gives us the amount that we have to take 1 part of nitrogen, we have to take 3 parts of hydrogen, and it is going to produce 2 parts of ammonia. So this gives us a ratio, that the reactants are reacting in a ratio which is 1:3, and they are going to produce certain amount of a product. So this stoichiometry works best in balanced chemical equation in a way that it finds out that what is the ratio of each reactant that are needed to produce that product. And there is another interesting fact to that if I want to produce a certain amount of product, so in order to produce that certain amount of product, I'm well aware from the balanced chemical equation that the reactant must have 1:3 of the reactants to produce a certain amount of product. So our desired product will be calculated in a way that it will find out that what amount in 1:3 ratio of those reactants are needed to produce the desired product that we need. So this is how balanced chemical equation works 2 ways. First, it gives you a scale. Now this balanced chemical equation will act as a scale, or you can say that as a recipe. So this scale is like 1:3 of the reactants we needed to produce a product. So if any amount of product that we are going to produce, we need that reactants in a 1:3, which is coming from a scale which is a balanced chemical equation. This is the beauty of balanced chemical equation, and this is the beauty of the stoichiometry, that it helps a scientist to work with small amount of substances to produce a product that will help them to not waste the energy, to not waste the chemicals, to not waste the time, and they should achieve their targets to produce a good quantity or good quality results. Now, let's understand mole. And we will come back to this topic again, but first we need to look into the basic things. So let's find out moles. What are moles? So moles are basically the numbers. How this is a number? There is a very good example to understand this relationship of moles with the numbers, and that is, we know that there is a term dozen, and whenever someone says that I have dozens of these things, or dozens of pencils, or dozens of apple or oranges or bananas, then one has a clear idea that it should be 12 in number. That's what dozen means. And if someone says 2 dozens, this means that that should be times 2. If we have 2 dozens, this means this is going to be double amount. In the same way, when someone says pair, so everyone has a very good view and very good idea that it should be 2 in number. So if we say 2 pairs, this means that we should have 2 times of the amount which comes in a pair, which is 4 in number. So This is how dozen and pair talks about the number of substances we could have. In the same way, we have moles. So when we say moles, this means that 1 mole, or mole, actually, mole, this is equals to 6.02 times 10 power 23 number of particles. This figure is known as Avogadro's number. Avogadro's number. And how these numbers are found? So the scientists work on a paper, some theoretical equations and the equations and the mass calculations and some calculations. They found out that Avogadro's numbers should be like 6.02 times 10 power 23, which has its experimental evidence coming from one of the Faraday's experiment. And in that experiment, he found out the exactly same number. So he said that Avogadros who have calculated that number on a paper has its practical application and got the same number from the Faraday's experiment in an electrochemical cells. So it proves the same amount, same number. So this becomes a constant. This number is a constant number. Why we call it a constant number? It's the same way that dozen is always 12. Dozen shouldn't be 13 or 14. So it's the same way mole has its number, which is 6.02 times 10 to the power 23, which is a constant Avogadro's number. Now let's look into that. It is talking about the number of particles. So what are particles? So particles could be charged bodies like ions. So they are the charged bodies. And particles could be neutral bodies like molecules. So they are neutral. The particles could be atoms. They are also neutrals. So they are neutral, and we have charged particles or charged bodies which are ions. So all of them, they comes under the heading particles. So if I have 1 mole of sodium ion, this should be equivalent to 6.02 times 10 to the power 23 ions of sodium, 1 positive ion. And then we have, if I have 1 mole of chloride ion, then this is also equivalent to 6.02 times 10 power 23 ions of chlorine, 1 negative. In the same way, we could have 1 mole of oxygen molecule. So this is also equivalent to 6.02 times 10 power 23 molecules of oxygen. And in the same way, if I have 1 mole of carbon atoms, this means that this is equivalent to 6.02 times 10 power 23 atoms of carbon. So if I have 1 mole of any particular particle, they will have the same number of particles all the way. That is how this is a constant number. Let's look deep into this concept of moles and Avogadro's numbers into conversion. When we talk about interconversion, this means that we have a scale, and that scale tells us that 1 mole is equivalent to 6.02 times 10 power 23 particles. So if I have some other number of particles, that will be some other number of moles. It's like this. If I have 10 of the apples, it will be some ratio of the dozen. It shouldn't be 1 dozen. It should be less than dozen. in the same way, if I have particles which are less than or greater than this constant number, then it should be some greater number of moles or lesser number of moles. Let's find out how. There is this, let's say we have 3.12 times 10 power 24 particles. The question is, what number of moles are there? What number of moles are there? And 3.12 cross 10 power 24 particles. So we are going to find out that. Let's say 1 mole is equals to 6.02 times 10 power 23. Let's take a ratio. So 3.12 times 10 power 24 will be equivalent to x moles. So we have a convention that these are multiplied together and these are multiplied together. Let's put it into an equation form. So x times 6.02 times 10 power 23, this is equals to 1 mole times 3.12 times 10 power 24. So x is equals to 1 mole times 3.12 times 10 power 24 divided by 6.02 times 10 power 23. Let's do a little calculations. So 3.12 times 10 power 24, this is divided by 6.02 times 10 power 23. So what answer do we get? We get 5.18 moles. So you got your answer. That this is equals to 5.18 moles. There is another way to calculate this, and which uses a formula, and that is moles which is equals to given number of particles divided by Avogadro's number of particles. So the given number of particles are this one. They are the given number of particles. And Avogadro's number of particles is what we have to memorize. So given number of particles, let's fill in the given information. So 3.12 times 10 power 24 divided by 6.02 times 10 power 23. The answer will be the same, 5.18 moles. So you could use two methods. You will have method number 1 that uses ratio, and you have method number 2 that uses formula. So however suits you best, you can use that method and you will end up with the same answer. Now let us look into other interesting facts about moles and Avogadro's number. When we say that 1 mole of oxygen molecule, this is equals to 6.02 times 10 power 23 oxygen molecule. There could be a question that we have this oxygen. This is made up of two atoms of oxygen, right? So how many number of atoms of oxygen are there in 1 mole of oxygen molecule? Question is, how many number of atoms are there in a molecule of oxygen? In a molecule of oxygen, this means that they are talking about 1 molecule of oxygen. So 1 molecule of oxygen is made up of 2 atoms of oxygen. This means that 2 moles of atoms of oxygen. So it will contain 2 times the Avogadro's number of oxygen atoms, like this. 1 mole of oxygen contains 2 moles of oxygen atom. So we are talking about the number of atoms. We are not talking about the number of moles of atoms. When we say number of moles of atoms, so we just said 2 moles of oxygen. When we say number of atoms, so we are talking about the number of atoms, the count of atoms in Avogadro's number. So 2 times the Avogadro's number, because 1 mole of oxygen atom contains 6.02 times 10 power 23 atoms of oxygen. So 2 moles will contain 2 times of 6.02 times 10 power 23. So this could give us a relation that whatever the molecule we have, the number of atoms present in there times the Avogadro's number will be the number of atoms which is present in a molecule of oxygen or in a molecule. Let's say this stands for N and this stands for Avogadro's number. So N times the Avogadro's number. In a molecule, we have N times the Avogadro's number of particles present in them, or N times the Avogadro's number of atoms has made 1 molecule, which again comes out to be the same Avogadro's number. That's a very interesting fact. You see, let's say we have a box, and in that box we have 2 times 6.02 times 10 power 23 atoms of oxygen are present. This one is containing 2 times 6.02 times 10 power 23 atoms of oxygen. So this means that a double of the Avogadro's number of oxygen atoms are there. When they combines together and makes oxygen molecule. Now you see that the number of atoms, they become half. Like now this is 6.02 times 10 power 23, because they combine together to form a molecule. So the number remains constant. The amount of oxygen atom here, which is 2 moles of oxygen atom, they combines together to form 1 mole of oxygen molecule. So there is a dramatic decrease in the amount of the particles present, and that dramatic decrease tells us that the 2 times the number of atoms present, they combines together and forms a molecules, but that molecules will have the same Avogadro's number of particles. I am sure that you are now quite aware of the fact, and you have now well understood what does this means actually? That the number of particles that makes the molecules will again end up with the same number of Avogadro's number. Let us take another example. We have water. We have 1 mole of water molecule. This must contain 6.02 times 10 power 23 molecules of water. And water is made up of 2 moles of hydrogen atom and 1 mole of oxygen atom. So in total we have 3 moles of particles, right? The identity is different, but we have 3 mole of particles. Now these 3 mole of particles means that in a container we have hydrogen atom, which are 2 times the Avogadro's number because there are 2 moles of hydrogen atom, and we have 1 mole of oxygen atom. So Avogadro's number of oxygen atom. Now when they all combine together, so basically we have 3 times the Avogadro's number of particles in here. So when they combine together to make a water molecule, now with each oxygen there are 2 hydrogens attached. You see, there are 2 hydrogens attached to each of the oxygen. Now what will happen? That makes 1 molecule of water. So the whole number concises to add it to 1 mole of water molecule, which is equivalent to Avogadro's number of water molecule. I hope we are clear about this moles and Avogadro's number interconversion. There is this method number 1 to find out if we have some other number of particles, and there is method number 2. Both ends up with the same answer. And then we looked into at atomic level, means elemental level, and we see that in an elemental level how this number remains constant. And now we are going to talk about moles and mass interconversion. So there is a very beautiful mnemonic, and that mnemonic is, there is a triangle, and this triangle talks about the working of moles and mass interconversion formula. Number of moles, this is equals to mass divided by the molar mass. In order to understand mass and moles conversion, there is this definition which tells us that moles is expressed as gram atomic mass of a substance. Now, what is gram atomic mass of a substance? Let us look at the mass number. Mass number of an atom. The mass number of an atom is a sum of proton and neutron number, right? So we know that the mass of a proton is 1 AMU, and the mass of a neutron is also 1 AMU. AMU stands for atomic mass unit. Whatever the mass of proton is, that is considered equals to 1 AMU, which is atomic mass unit, which we again say that this is equivalent to 1 gram, right? So let's put into an atom. Let's say this is the nucleus of an atom. And it has the different color represents different particles. Green represents a neutron, which is a neutral particle, and orange represents a proton, which is a positive particle. Now, how many protons and neutrons are there? So we have 6 of neutrons and we have 6 of protons. So 6 of protons and 6 of neutrons. So each 6 will be equivalent to 6 AMU, and 6 AMU is equivalent to 6 grams. So 6 and 6, when they add up together, they makes 6 AMU, 6 AMU, which is equals to 6 grams, 6 grams, and they made up into 12 grams. This means that if I have 1 mole of carbon atom, this is equivalent to its gram atomic mass. So what's its atomic mass? This atomic mass is talking about the mass number. And what is this mass number? This is talking about the sum of proton and neutron number, which is 12 grams. So 1 mole of carbon atom, this is equals to 12 grams of carbon atom. The formula can have another member entered to it, and that is AR along with MR. So AR stands for the mass number. This mass number is also abbreviated as AR, atomic mass, relative atomic mass, AR, relative atomic mass. So mass number. In the same way, if I have 1 mole, of water molecule, what is the mass of water molecule? So let's look at elemental level, the way they combine, and those mass are added together and they will give rise to the compound mass, which is the mass of 1 molecule of water. So here we have oxygen atom, which is bonded to 2 hydrogen atoms. So this is hydrogen. It contains only 1 proton. There is only 1 proton. And in oxygen, we have 8 protons and 8 neutrons, right? So if we add up the mass of these protons and neutrons, so in total we have 10 protons and we have 8 neutrons. So 10 proton means 10 AMU and 8 neutron means 8 AMU. This means that this will be 10 grams, this will be 8 grams, and they makes 18 grams. So 1 mole of water molecules, this is equals to 18 grams of water molecule. Since this is the mass of a molecule, not the atom, so this is abbreviated as or equivalent to MR, which is also known as molar mass, or is also known as molecular mass. However you pronounce this, MR is molar mass or molecular mass. This is the mass of a molecule. Now, we are quite well aware that if we have a gram atomic mass of a substance, that should be equivalent to 1 mole. But if we have less than the gram atomic mass of a substance or greater than the gram atomic mass of a substance, then that should not be equals to 1 mole. That should be some other number of moles. Let's find out that. Let us do an example to reinforce our understanding. You are provided with 32 grams of carbon atom, and you need to find out what moles of carbon atoms are there. So we are going to find out that what moles of carbon atoms are there. We have a pretty good convention, and that tells us that if I have 1 mole of carbon atom, this is equals to 12 grams of carbon atom, which is a convention coming from the definition. So if I have, let's make it into a ratio. If I have 32 grams of carbon atom, it will make how many moles of carbon atoms? Let's find out X. So X is equals to diagonals multiplies, and then the one which is next to the X is taken to the other side and it becomes as a divided function. So I'm just writing it in a direct way. So 32, 1 mole multiplies by 32 grams divided by 12 grams. So when 32 divided by 12, what do we get? We get 2.66 moles of carbon atom. You see, when we have a different grams of carbon atom, which is not actually the gram atomic mass of carbon atom, then the number of moles will be different. So if you have a mass which is greater than the gram atomic mass, it will be a greater number of moles. If you have mass which is less than the gram atomic mass, then that will be less than the number of moles, which is 1 mole. So let's put this into the formula as well. The formula tells us that this small m stands for the given mass. This small n is used for moles. And this mr is actually the molar mass. And this AR is the atomic mass. So here we can use molar mass or atomic mass according to the substance provided to us. If they talk about the molecules, then we will be using MR here in the triangle. And if they talks about the atoms, then we are going to use the atomic mass, which is AR, in place of MR. So here we are talking about the atoms. So the triangle tells us that if I pick number of moles as a subject that I need to find out, then the other two subjects will work as this. They are one above each other. They will make a shape of mass over atomic mass. And if I make mass as a subject, then they are in front of each other, number of moles and atomic mass, then they will multiply with each other. If I take AR as a subject to find out, then the one above each other, like mass over number of moles, it will become. So it will give us a good shape to memorize it. How to memorize it? We can memorize it in terms for atomic masses. We can use this as M and A, and for molecular mass this could be M and M's. So M&M's, the sweets. We will be finding out one example with the molar mass. So number of moles is equals to mass over AR. So mass is this given mass. This is the given mass. So mass is 32 grams, and AR, this is coming from here, which is a gram atomic mass of carbon. This is what appears in a periodic table. This value what appears in the periodic table. So 32 over 12, we pretty much end up with the same answer. 2.66 moles of carbon atom. Yeah, we did it. Now let's look into one example for the molecules. We have example number 2. Now we are provided with let's say 40 grams of water. So the question is, what moles of water are there? Or you can say that what number of moles of water are there? Let's find out. Again, we have this triangle, and the triangle tells us that this is mass. Now we are talking about the molecules, so MR, and number of moles. So if I take, so that makes a mnemonic, M, N, M. That's sweet. You can memorize it like this, M&Ms. So M, N, and M. So we place it in the triangle like this. So mass, if I take mass as a subject, then number of moles and MR, they are in front of each other, so they are going to multiply. This is how this triangle works. And then we have number of moles as a subject. Then the mass, the other two members of the equation, or the other two entities, they are one above each other, so that makes mass over molar mass. And if I make MR the molar mass of a subject as a subject, then other two entities, they are one above each other, so mass over number of moles. This is how this triangle works, and it helps you memorize, and it helps you rearrange the equation to get the one that is missing. And there is another method, which is a ratio method. So we will be using both these method, and whatever method works out best for you, you can use that method. So let's find out what amount of number of moles of water are there in 40 grams of water. So there is one way that you first find out the MR of water, the molecular mass of water. And how do we find it out? We multiply the number of atoms with its atomic mass, which is 1 for hydrogen. This is AR of hydrogen. Plus, we have 1 atom of oxygen, so we multiply 1 with the AR of oxygen, which is 16. This is AR of oxygen. So doing the math, we will end up into the same 18 grams per mole of water, right? So 1 mole of water molecule is equivalent to 1 mole of water molecule. This is equivalent to 18 grams of water molecule. So if I have 40 grams of water molecule, then what mole of water molecules are there? That will become X. So let's make it into a ratio. So X is equals to 40 grams times 1 mole divided by 18 grams. So we get 2.22 moles, because this and this will be cancelled out. We are just left with moles as a unit. So X is 2.22 moles, which is the number of moles of water which are present in 40 grams of water. Now that is your method number 1, which is a ratio method. Now let's use the formula method. The formula method tells us that this is the given mass, and this M stands for, or talks about, the given mass. N stands for number of moles, and MR stands for the molar mass, right? So method number 2, number of moles, that is the subject which is need to find out, which is equals to the given mass divided by the molar mass. So given mass is 40 grams, and the molar mass tells us, which is the MR, which tells us that this is equals to 18 grams per mole. That is the basic unit of the molar mass. So we have 18 grams per mole. We have 18 grams per mole. So 40 divided by 18, we end up into 2.22 moles again. So we see that the both method ends up with the same amount of answer, and whatever method works best for you, you can use that.